the respective orbitals. Right? I can view this state, many determinant state, now multi-configurational state, in this case only two configurational. I want to view it as state with fractionally occupied orbitals. This is like, well, we can vaguely think of it as if we have Fermi distribution at finite temperature, not at zero temperature, where it's like a stepwise function, step-like function, and it separates Fermi level, separates occupied and strictly empty states. But if we introduce some finite temperature, pretty high temperature, it should be, and then we will have fractional occupations on average of the orbitals. So it will be difficult to tell which orbitals are empty, which are occupied, but we have now fractional orbital occupation numbers. So yeah, they are.
Yeah, this would work in the case of H2, but if you have a more complicated systems,
yes,
you have a lot more.
Yes, that's correct. That's correct.
What would be, that's a kind of becoming approximation or
well, this is only for H2 molecule. In fact, as we will see, at the level of density functional theory, ensemble density functional theory, there are not too many fractionally occupied orbitals that occur.
Yeah.
In the case of standard wave function methodologies, we will have technically at the full CI level all orbitals, I mean, from the lowest to the highest. Even we don't have now unoccupied orbitals at all. All orbitals are occupied. Some are stronger occupied with the occupation numbers closer to 2. Other orbitals are very weakly occupied, occupation numbers near 0, but they are all occupied. So, and this is, I think, important realization in this field, multi-configurational wave functions. It is often used in analysis of the multi-configurational wave functions. So this will be, in the case of CASP SCF, for example, these occupation numbers will be natural orbital occupation number. They are typically associated with that. But I focus here on a very simple situation, only two configurational wave function, where interpretation of these occupation numbers is rather simple. On average, I have, let's say, contribution of this configuration with this weight and contribution of this configuration with this weight. And these weights are, because the electronic configurations have this and that have fixed occupation numbers, 2 in sigma u or 2 in sigma g, I can associate these weights with fractional occupations of orbitals, as if these two orbitals were fractionally occupied. This is in some way, let's say, model description, right? But I can always introduce such a concept as fractional occupation numbers of the respective orbitals, right? And in this simple two configurational wave functions, they will be given by the squares of their coefficients of these configurations in the wave function. Or in other words, the energy of the ground state, lowest state, which corresponds to this wave function, will be given by this expression, where I will have kind of weighted sum of the energies of two configurations with sigma g orbital doubly occupied, this one, and with sigma u orbital doubly occupied. In front of them, I will have, of course, well, in this case, halves of the occupation numbers of the respective orbitals, these fractional occupation numbers. And there will be some coupling term between the two electronic configurations. This coupling term originates from electron-electron interaction, electron-electron repulsion. Yeah, but it is negative because we have solved this equation, and the contribution of this term will have minus sign, right? So it is negative. But the this term in front of the weighting factor, in front of the exchange integral, is given by simply by square root of the product of the two fractional occupation numbers, right? So we have the coefficient 2 C node node C2 node. If we realize that each one of them can be represented as square root, we will end up with this expression. I mean, that square root of ng is square root of 2 times C node node, and square root of nu is square root of 2 times C2 node, right? So we take product of the two square roots and we end up with exactly with this term. So this is alternative expression instead of solution of the quadratic equation.
What if, yeah, in that case, yeah, n is a square. Yeah, okay. So in that case, it's okay. But sometimes the coefficient can be negative, but then you don't actually use coefficient. You take the square root of it.
Right.
So in that regard, that's okay. Yeah.
Mm-hmm. Yeah, that's correct. If I, well, if I use this, say, doubly excited configuration to obtain its energy, then the only difference will be that inverse sign, so plus instead of minus in front of this term. Mm-hmm. This is very simple because the eigenvalues of of a simple 2 by 2 matrix are always, say, cosines and sines. Cosines of some angle are on the diagonal, and on the off-diagonal terms are minus sign and plus signs. So cosines, sines. And I will see simply that if in one case, in the case of ground state, I have cosine times minus sine, then in the case of doubly excited state, I will have cosine times sine of certain angle, right, in here. So therefore, I have for the ground state minus, for the doubly excited state, I will have plus here. So this will, in general, give me both solutions, E node and E2, of the 2 by 2 secular problem. And I can get rid of even of the exchange integral and convert this expression into this, where I use only energies of single determinants with some specific orbital occupations, of course. So what we have here has an exchange integral on its right-hand side, but the exchange integral can be obtained as difference between the energy of, let's say, broken symmetry, broken spin symmetry, of course, a single determinant. I have only two orbitals in a hydrogen molecule, right? Sigma G and sigma U. Sigma G with spin up and sigma U with spin down electron. It can be other ways, other way around. The energy expression for this broken symmetry, spin unrestricted, let's say, configuration will be the same, will remain the same. I'll explain. According to the Slater rules, I will have, let's say, energy of the orbital G, 1 sigma G, plus energy of orbital 1 sigma U, plus Coulomb repulsion between the two electrons. Because both electrons have opposite spins, there is no exchange contribution. Exchange integral here is missing. For the triplet electronic configuration, I will have the same epsilon G and epsilon U, orbital energies of this and that orbital, the same Coulomb repulsion between the electrons, because Coulomb repulsion is insensitive to the spin. However, now, because both spins are parallel, I will have exchange integral, minus exchange integral. So this electronic configuration is lower than that in energy by this amount, by exchange integral. Therefore, I can take, let's say, difference between the two, broken symmetry, singlet. Oh, it's not singlet, it's mix of singlet and triplet, as you know, and triplet state, high spin triplet state, to obtain the energy of, not the energy, the value of this exchange integral. And therefore, I can convert this expression into that. And this expression has advantage that it's linear in energies of several electronic configurations. So the main configurations, which are doubly occupied sigma g orbital and doubly occupied sigma u orbital. So these are my main configurations, minus coupling term, which is given by the energy difference between broken symmetry electronic configuration and high spin electronic open shell electronic configuration. So this is very simple, and it has advantage that it is linear in energies, and I mean it's expressed in energies only. And this equation, which I showed you before, works exactly as solution of the quadratic equation. So it produces correct, this green curve, correct dissociation curve for the hydrogen molecule. And you can see how the occupation numbers of sigma g and sigma u orbitals vary with distance between the atoms. So near the equilibrium bond length, up to this point, both remain, let's say, canonical, 2 and 0. So doubly occupied sigma g orbital and empty sigma u orbital, which intuitively this is the correct picture near the equilibrium geometry. Now, as I stretch the bond beyond so-called Coulson-Fisher point, the occupation numbers of the two orbitals depart from their, let's say, canonical values, 2 and 0. And already at 2 angstrom, I will have, let's say, in sigma u, almost half electron on average in sigma u orbital. And in the sigma g orbital, I will have approximately 1.5 electrons. So it's like I stretch the bond and I transfer some fraction of this electron pair to higher lying orbital. And it will lead to lowering the energy compared to the energies of the original configurations. So this doubly excited and ground state Hartree-Fock electronic configuration. In the dissociating limit, I will end up with 1 and 1 occupation numbers, equal occupation numbers, as it should be, because both electronic configurations with doubly occupied sigma g and with doubly occupied sigma u orbital, they become degenerate. Therefore, their occupation numbers become equal. Right? So this is intuitively, let's say, correct picture of bond dissociation.
But you also have singly occupied ones too, not just the doubly, because in your expansion.
That's correct, but these singly occupied orbitals here, they do not contribute to, they do not directly contribute to the density. And therefore, they do not.
Why?
Because density, if we realize that, well, if you use the same orbitals for alpha and beta electrons, so spin restricted description, then the density, total density given by this configuration and total density given by that configuration are the same.
Oh, they are subtracted. Oh.
So they, yeah, exactly. They will simply disappear in the expression for the density, and the density will be given only by average sum of these two densities of these two configurations. Yeah, therefore, the singly excited, they do not contribute at this level of description.
But you need those, right? During the...
I need them to obtain the exchange integral, right? So, and in fact, I can obtain these two parameters, Ng and Nu. There is only one free variational parameter. I can treat them as variational parameters, Ng and Nu, fractional occupation numbers. There is only one free variational parameter because Ng plus Nu will be always 2, right?
No, that one.
because of this constraint, I have only one free variational parameter. I can minimize this energy expression with respect to any one of them and obtain the other from this formula, from this constraint.
But then you need 4 different energies, right? Energies you can calculate.
Yes, exactly. But 4 different energies I obtain from the known orbitals.
Yeah. That's
well, yeah, I need energies of at least 4 configurations. But I minimize the energy of this expression with respect to only one variational parameter, either this or that. More convenient to optimize it with respect to NG as a matter of experience. But can be any.
Yeah, because of this is a close, I mean, the spin restricted, so you probably don't need to distinguish broken symmetry or the correct symmetry, right?
Yes. I don't need
the other combination, right?
Right. Yeah.
You just need energy, so that's why.
Yeah, exactly. I only interested in energies at this moment, and I know that this term, if I use the same expression for the density, because each one of them is expectation value of the Hamiltonian operator with respect to certain wave function. For example, wave function corresponding to this determinant, that determinant, this determinant, or W occupy this determinant. Yes, so these are expectation value of the Hamiltonian. I can take expectation values of the density operator, and in that case, I will see that this term simply vanishes, and I am left with only these two, where this will be density and density, rho and rho. Rho of this determinant, rho of that determinant. With this exactly the same coefficients in front of them. So the energy and the density can be represented with the same basic formula. And I will use this formula in the following. So this we have already seen that the occupation numbers of these orbitals, they start deviate from 2 and 0 values approximately at the point, if you remember from the previous slide, where the denominator and the numerator of the perturbational second order energy become approximately equal. At that point, they start deviating from their 2 and 0. And beyond this point, perturbational theory is no longer valid, and one needs to use quasi-degenerate perturbation theory, which I reformulated in terms of simply energies of single slater determinants. And this was a very useful expression, which lets me to apply the same idea in the context of a density functional theory. Yeah.
So sorry for interrupting.
No worries.
Yeah, before moving on to the density functional theory, I have a question in previous slide.
Yeah, this slide.
Yeah, right. I'm not clear about advantage to get exchange integral by the subtraction of two energies. Can you explain more about it?
Yes, I'm going to explain it a bit later. I can tell you right away now. Of course, if we want to stay within, let's say, MC-SCF methodology only, then this expression has no advantage before that. However, if we want to switch to density functional theory, then we can, at the DFT level, we can easily calculate energy of this configuration. We can calculate energy of that configuration, of these and that, at the DFT level. But if we look at this expression, how can we evaluate at the DFT level this exchange integral? Strictly speaking, it's not defined within a simple Kohn-Sham DFT. We would have to do some tricks to obtain it. Probably we would end up with the same expression. It has been done, in fact, in, for example, in broken symmetry, when you try to perform some approximate spin projection at, say, broken symmetry UDFT, spin unrestricted DFT, broken symmetry level, you also end up at expressions which involve differences between broken symmetry solution and triplet state, for example, or high spin state. So-called, let's say, Nudelman, say, approach, right? Quite often used to evaluate from, well, energy splittings in metal complexes from DFT calculations. So this expression, of course, has advantage because it's simpler to calculate at the level of wave function theory. However, this expression has advantage at the level of density functional theory, because at the DFT level, we simply don't know how to express the exchange integral. Yeah, we can try the same trick, but we end up with expression such as this, right?
Thank you.
Right. So that's my main motivation to switch over to energies only and nothing else.
Michael. So we already have about 1.5 hours.
Yes,
Are you okay?
we do.
You
so
okay?
That's why I asked for more time.
Okay. I mean, the other people's okay. I mean, oh
Well,
yeah.
I think that half an hour will be sufficient, because after that there will be only one more or less say difficult part. The rest will be simply some sort of illustrations, illustrating examples. One of them I can skip these because that was one of the model systems.
So let's keep going for about. Do we need a break or?
No, it's okay.
Okay, let's keep going. About 3 minutes more, right, Michael?
Yeah, I don't need break. So
okay, let's go. Let's go then.
Let's go on then. All right.
All right.
So one of, say, illustrating examples is so-called automerization of rectangular H4 molecule. So we have H4, and there is a short side of this rectangle and a long side, and we simply, through square conformation, through geometry, we end up with, say, another like 90 degrees rotated, when the short side of the rectangle becomes longer and long side becomes shorter. So this can be described with one angle. If we keep this radius fixed, we can describe a potential surface with one angle, for example. And at the square configuration, angle theta 90 degrees, both electronic configurations with W occupied, well, in this case, B2U orbital or then empty B3U orbital. So they are combinations of bonding and anti-bonding orbitals of the two H2 units. The two configurations become degenerate, W occupied this or W occupied that. They become degenerate, and therefore single reference description breaks down. So we have now, with the two configurational expressions that I showed you before, we have smooth curve along this automerization, let's say, coordinate, and we see that the occupation numbers of the respective orbitals, they smoothly vary between 2 and 0, right, depending on. So this is one of the examples of symmetry forbidden reactions. It's very simple. Chemically, it's probably meaningless. However, this illustrates symmetry forbidden reaction. At the beginning, we had W occupied B2U orbital. In the end, we have W occupied B3U orbital. It was empty in the beginning and it becomes W occupied. That was, the orbital was W occupied and becomes empty in the end. So according to Woodward-Hoffman rules, such reactions are symmetry forbidden. So chemically seen, they would be very difficult. We'll have very low probability of reaction in the ground electronic state because of very high energy barrier. And the barrier, as you see, indeed is around maybe 70 or 80 kilocalories per mole at this level of description. Well, it will be probably even larger than that, because I start from from angle around 70 degrees, not two isolated hydrogen molecules. But anyway, this will be very, very high barrier between the two, say, reactants and product, between the two conformations of the molecule. But the main point is that with two configurational description, we can describe this barrier, so smooth transition between the two configurations. But with single determinant approximation, we would not be able to do so, right? So if we keep the occupation numbers fixed, well, of course, at some point, the Hartree-Fock description would break down, and it would converge not to this configuration, but to that. However, that's artificial. That would be totally artificial. With two configurational, we can smoothly describe. So another example of a symmetry forbidden reaction, or similarly, this is also sort of bond breaking, breaking of pi component of the double bond of ethylene molecule by torsion. So imagine that we twist the two CH2 groups with respect to one another while keeping the bond at the same length. I don't care about the bond length, this. I can keep it at the equilibrium value, but I perform twisting of the two CH2 groups. In this case, again, pi orbitals, which were pi bonding orbitals, were doubly occupied in the beginning. Pi antibonding orbitals were empty in the beginning, but at around 90 degrees of torsion, the two electronic configurations, doubly occupied pi bonding and doubly occupied pi antibonding, they become degenerate. And standard single reference description would produce simply a cusp at this crossing point between the two configurations. But two configurational description produces smooth potential energy curve. So this is another example of, again, symmetry forbidden reaction or dissociation reaction. So two configurational description at this level, well, for this system is sufficient to describe correct shape of the of the potential energy surface. Although the energies may be not very, say, accurate, because I did not include, at the wave function level, I did not include the most, say, one of the important ingredients in the energy, so-called dynamic correlation. Right, so...
Yes,
yeah, right.
May I ask?
Yes, of course.
It was a question. I want to ask. You stress always it is non-dynamic relation. Yes. What? Yeah. Could you also basically said that the principal difference? What? How we can go to dynamic correlation from here? Or dynamic and non-dynamic correlation?
Right. To go to the dynamic correlation, I would need to, well, at the wave function level of description, I would need to probably introduce some kind of perturbational description of the dynamic correlation based on the multi-configurational wave function. So this would be MC-SCF or two configurational TC-SCF, and I would need to develop some kind of two configurational MP2 or two configurational PT2, better to say, perturbation theory methodology. At least the lowest or the second order contribution to the dynamic electron correlation. So this is similar to CAS-SCF, CAS-PT2, right?
But you want to do it with the DFT for the dynamic.
With DFT, DFT, in fact, what is the advantage of that, say, energy expression here? If I treat these energies as DFT, energies of DFT, say, single determinant, Kohn-Sham determinants with different orbital occupations, right? Then DFT automatically includes dynamic correlation into the description, right? So the
each correlation functional contains supposed to be.
Correlation functional is supposed to cover these. That would be the advantage of using DFT energies instead of simply.
On top of that, on top of that, there's a multi-configurational feature include the non-dynamic. So but he hasn't talked about the DFT yet. So
Mhm.
Yeah, this is
your question, yeah.
illustration